Welcome back, everyone. We're going to go ahead and cover section 6.4. We're going to talk about graphs of the sine and cosine functions. Now, through the next couple weeks, we're going to kind of look at the different trig functions, meaning we're going to identify the sine, cosine, tangent, cotangent, secant, cosecant. And we're going to evaluate the properties and how, if we apply integers either to the front or inside the brackets, how does it affect the graph? And are we able to look at a graph and then convert that graph into a mathematical equation? Well, let's start off and take a look. We know by default that our sine wave starts at the region 0, 0, goes to pi over 2, then comes back down to pi, 3 pi over 2, and then it reaches 2 pi. Now, this is based upon sine of x alone, following the interval of 0 to 2 pi. When we look at a sinusoidal wave, we say that it is from negative infinity to infinity, meaning it never ends, no matter how you look at it. We've identified this already, the properties of the sine. But as a good refresher, we can go and say that for the range and the domain, they consist of all real numbers. And in the range's case, it goes from -1 to 1. We know that the x-intercepts are found on the negative pi, 0, pi, 2 pi, points of the axis. And this will continue on down the road in both directions. We also know that the maximum 1 value occurs at pi over 2, 5 pi over 2, etc. Also, the minimum value occurs at minus pi over 2 and 3 pi over 2. So let's go and look at the graph function of the form of y equals a sine wx. So we've got a graph here, y equals 3 sine of x. And we want to use some transformations. A few things that you need to be aware of is that the value in front, if we go back to this, look at this equation, we have a sine wx. A stands for the amplitude. So in this case we have an amplitude of 3. And they're going to go and draw this out for you. Notice this is the standard sine of x. Yet, when we do our multiplied by 3, it doesn't change the points of where it corresponds on the x-axis. It does change the points on the y-axis, meaning that it amplifies it by 3. You always start at the point of origin, which is at 0, 0. And move up to the amplitude in the positive direction and in the negative direction, because the amplitude is taken based upon the absolute value. Here, we're going to go and graph y minus sine of 2x. Now, we have to be careful because we've got a minus sign in first. Step back real quick. Notice that we start at the origin of 0, 0 on a standard y of x, and we go increasingly till we get up to 1. Once we get to 1, then we start on a decreasing slope. Well, in this case here, where we start off with a negative, we start at the origin like we did before at 0, 0, but instead of going increasing, we automatically start decreasing. As you see here, sine of x. And now we're in the decreasing mode over this interval of 2 pi. Now this 2 pi is based upon only a sine of x. So you would have to assume that this was just sine of x, a minus. But because we have a 2 in there, it changes it quite a bit. What it actually changes is that it causes the wave to be compressed. So instead of going from 0 to 2 pi for one full revolution. In this case, we're going 2 full revolutions within that same period of 2 pi. The graph of cosine, a little bit different than the graph of sine, because why? We start off in the origin of 0, 1. We still start on the y-axis, and then we start to follow it down. But in this case here, what are my major points? Again, we have 0, pi over 2, pi, 3 pi over 2, and then finally back to 2 pi. Just like the sine, it falls on the interval of negative infinity to infinity. It also has a domain of all real numbers, also has the range of all real numbers from -1 to 1 exclusively. Here, we have the x-intercepts fall on the pi over 2 negative, pi over 2, 3 pi over 2, and 5 pi over 2. So let's evaluate the function of y equals a cosine using transformations. Well, again, we have a 2 here. So we know it has an amplitude of 2. Cosine 3 to the x. Now, the way we calculate the period in this case is it's 2 pi over the value here. We have y equals 2, so we already said that this right here is the absolute value. This is equal to my amplitude. Here, we take this value, whatever it is, and we put that under the 2 pi. In this case, there's no further math function that I have to do at this point, so I can say that my period goes from 0, 0 to 2 pi over 3. Now, I need to do something else besides just figure out what my period is. I need to be able to divide this into 5 different, or give this into 4 different quadrants. So, how do I do that? We take it, divide it by 4. Rule of thumb is we inverse the second number, in this case it's 4 over 1, and multiply. So we'd have 2 pi over 3 times 1 over 4. This comes 2, that becomes 1. Therefore, each interval point is a pi of 6 from the original origin of 1, 0. Let's go ahead and go back to the equation. Let's see how close we were. Here's our original y of cosine of x. Starts off with the origin of 0, 1, follows it down to pi, back up to 2 pi. Now, we had a 2, so we're going to go ahead and stretch it vertically by a factor of 2. The points along the x-axis never changed. The y's did only because of the amplitude. So now let's go and replace the x and look at it by a 3x. And now we're doing a horizontal compression, meaning we're putting more inside the package. And notice we had stated that it's on an interval of pi over 6. And what do we see? The first point along the x-axis is pi over 6. 2 pi over 6, which breaks down to 1/3. 3 pi over 6, 1 over 2. 4 over 6, 2/3. 5 pi over 6, and then finally 2 pi. Now we have two different graphs here. We have one that's a cosine of x, and then we have one that's a cosine of minus 2 pi. What that is actually saying is that it's called a phase shift, meaning that it moved across the x-axis by a shift of negative pi over 2. If we were to replace this with a sine wave of x, it would be identical. So therefore, what we can say is the sine of x is equal to the cosine of x minus pi over 2. And if you were to graph it out on a calculator, this is exactly what you would see. They wouldn't see any difference as far as the shift goes. So how do we determine the amplitude and the period? Well, I've been kind of doing that for you this whole time, so it'll just kind of be a little bit of a refresher from 2 to 3 minutes ago. We have the y is equal to cosine. We start off at 1, negative 1, 1, negative 1. Here we have the amplitude of 2, so we go ahead and go up to 2. But the points on the x-axis never changed. They are still current to what they were before. So therefore we can say that the y equals a sine of theta, where a has to be greater than 0. We also have a period of 2 pi, meaning that it starts at the origin of 0, 0 and goes all the way to 2 pi. Cosine, on the other hand, starts at the origin of 1, 0 and goes to the origin of 2 pi. In this case here, they went ahead and put a 3x in the center here. What do? We take that 3, we take 2 pi divided by 3, that'll give us our pi over 6, and then we mark out each point from there on out. From this problem, we've identified two theorems. Both that sine and cosine have an amplitude that's placed in front and identified here by A. And then we have a period. And the period is identified by what's in the center between these brackets. And it either is going to increase, meaning stretch it across the x-axis, or it's going to push more closer together along the x-axis. So your amplitude directly affects the y-axis, and then stuff in between here directly impacts the x-axis. So determine the amplitude and period of y equals minus 4 cosine 3x. Well, what's the first thing we do? We know the absolute value of 4 is 4. So therefore, my amplitude is 4. My period is 2 pi over w. In this case, my w is a 3. So it's 2 pi over 3. And that's it for this. Using the sinusoidal functions to graph sinusoidal functions using key points. So here, on a standard sine wave, on a standard cosine wave, we have the standard points of 0, pi over 2, pi, 3 pi over 2, and also 2 pi. As you can see, they've identified them here at the top of the screen. Your amplitude is 4. And now we're going to look at the period. We have a period of 2 pi divided by 2. Therefore, our period is equal to pi. Now, this is just one point. So now what do we have to do? We have to break it into 4 separate quadrants. So we're going to divide pi by 4. Once we've done that, we now have identified the different points on our graph. And then we can go ahead and draw the 5 points. And there you go. Let's take a look at another one. As you can see from the summary, with the steps of drawing a sinusoidal function, the first thing we need to do is determine the amplitude and the period of the function. Then we need to divide the interval into 4 subintervals of the same length. And then we need to use the endpoints of these subintervals to obtain the 5 key points on the graph. Now these endpoints are the standard points that we use when we first start out. That means being 0, 0 if it's a sine, or or 0, 1. So let's go and take a look at this example here. We have 3. 3 is my amplitude, because I'm going to take the absolute value. And then I also have a negative in front of that, which in this case, when we bring it up, you'll see it actually starts on a decrease instead of an increase. I'm sorry. So let's evaluate y equals negative 3 cosine pi over 4x. Well, the first thing I notice right off the bat is my amplitude is going to be 3. The next thing I know is that I'm going to have a 2 pi over 4 as far as my period. Like we said, the amplitude is 3. I then have a 2 pi over 4 equals 8. I'm going to divide that into 8 segments. I'm sorry. We're then going to go and divide that 8 by 4. So each segment is a length 2. So our points are at 0, 2, 2, 4, 4, 6, and then 6 and 8. And if we draw it out, there you go. Another example. So here we're going to use 5 sine 3x. Well, the first thing I know right now is my period is going to be 5. My period is going to be 2 pi over 3. And I'm going to take this, I'm going to divide it by 4 because I got 4 quadrants. And each interval point on the graph will be identified by pi over 6. And here you go. Now going backward is just as easy as going forward. When making the transformation from the equation to the graph, or from the graph to the equation. So let's take a look at this graph here. What's the first thing that you notice about it? Well, you notice it has an amplitude of 3. And in this case, we have a period from 0 to 1, which is in our case, 2 pi. The first thing that we notice about this graph is that we've got an amplitude of 3. We also notice that it starts at the very top. So we have 3 cosine, and the value that we're in question is the period piece. We know that we go from 1 full rotation because we go from 0 to a quarter of a circle to a half a circle to 3/4 of a circle to 1 full circle. So we can translate that one rotation or revolution as 2 pi. And therefore our final equation is equal to 3 cosine 2 pi of x. Let's take a look at a second one. What can we say about this graph here? Well, we know that the amplitude itself is 2. Now be careful, because as you look at this graph, it looks very similar to the sine wave. The only difference is that it starts on a down slope instead of an increasing slope. So because of that, I would say my amplitude value is negative, meaning it would be -2. My wave itself is a sine wave. And my period is on an interval from 0 to 4, which in this case is equal to pi over 2. So let's take a look and see if this is what they have achieved. We've got their amplitude is -2, their period is 4, therefore their final equation is -2 sine pi over 2 x. Not bad. Hopefully this was useful. And again, I will try to do a couple videos on the homework, so just in case you did get lost or confused, you can go ahead and ask me questions in class, or you can wait until the video lectures come out on the homework itself. Hopefully you guys have a good night, and we'll talk to you later.